Open any introductory chemistry textbook, and you will likely find a covalent bond defined as the sharing of electrons between two elements. This definition is usually paired with the duplet or octet rule, the idea that atoms complete a full outer shell of electrons to achieve a state of stability. But there is a logical flaw in this framing. Atoms are inanimate matter. They do not possess consciousness or desires, and they cannot want to complete a shell. The metaphor of sharing is a pedagogical shorthand. It masks the rigorous physical forces that dictate how atomic structures are built. To understand molecular structure, we look to the rules of classical electrostatics. Opposite charges attract, and like charges repel. Inside an atomic system, there are two charged players obeying these rules: the positively charged atomic nuclei and the negatively charged electrons. A chemical bond is a mathematical equilibrium established between specific, competing, attractive, and repulsive electrostatic forces. The exact distance between two bonded atoms is determined by these forces seeking out the lowest possible state of potential energy. The covalent bond is a dynamic electrostatic tug-of-war. We contract this tug-of-war by observing isolated hydrogen atoms approach each other. The graph on the right plots potential energy against internuclear distance. At extreme distances, electrostatic interactions are zero, corresponding to the 0-point line on our graph. As the atoms slowly drift closer, electrostatic forces begin to develop across the shrinking gap. At this range, each positively charged nucleus pulls on both electrons in the system. Repulsive forces develop simultaneously. The two nuclei push against each other, and the two electron clouds do the same. While both forces are present, the attractive pull between the nuclei and the electrons is currently stronger than the outward push of the repulsions. This creates a net attractive force that pulls the atoms together, causing the system's overall potential energy to drop. The initial bond formation is driven by a system naturally moving toward a lower, more stable state of potential energy. If a net force is pulling the atoms inward, what prevents them from collapsing into a single point? Consider a scenario where external pressure pushes the two hydrogen atoms incredibly close together. At extremely short distances, the repulsive interaction between the two positively charged nuclei becomes the dominant force in the system. This nuclear repulsion overpowers the attractive forces, stopping the inward momentum and pushing the atoms apart. On a potential energy graph, this physical limit appears as a steep vertical line surging into positive territory. This spike represents a state of high physical instability that the atoms naturally avoid. Nuclear repulsion acts as a barrier that prevents atomic collapse and defines the inner limit of molecular structure. Between the distance of isolation and the repulsion of collapse, the atoms find an optimum distance where the inward pull of attraction cancels out the outward push of repulsion. This specific internuclear distance is the bond length. This distance corresponds to the absolute bottom of the dip on the energy graph. For a hydrogen molecule, this balance is reached exactly at 74 picometers. This measurement represents the absolute minimum potential energy state for this system. In chemical systems, minimum potential energy is synonymous with maximum stability. This zone of maximum stability is known as the energy well. The bond exists as the geometric distance where opposing electrostatic forces reach a stable minimum energy stalemate. Every unique combination of elements has its own characteristic bond length required to reach this state of stability. We can estimate these lengths using the known atomic radii of the elements involved. Take the predicted bond length for hydrogen chloride. Hydrogen has an atomic radius of 37 picometers, while chlorine has a radius of 99 picometers. Adding these two radii gives us a projected internuclear distance. This calculation yields a predicted bond length of 136 picometers. The experimentally measured bond length for hydrogen chloride is 127 picometers. While these geometric approximations vary slightly from experimental values, they show that structural chemistry follows predictable electrostatic rules. The octet rule is a useful heuristic for balancing equations, but it is not a description of physical reality. Electrons are trapped within a mathematical energy well, held there by the balance of physical forces. This electrostatic tug-of-war exists within any molecular structure, maintaining stability through constant vibration. Analyzing matter through the lens of physical forces, rather than atomic intent, provides an accurate map of why atoms bind together.